to go a bit more into the technical details on Oniro. Not all of them, but basically like having a look at the technical architecture of the Yocto-based build system and build flavors we are having. So be welcome and join my colleague Andre and myself in going to look into that a bit more. So the agenda for today, for the next 30 minutes, basically, is that we will talk a little bit about the Yocto OpenEmbedded build system, how we are using it, or what it basically is. Then we will start into what we call build flavors. I will go into that in the details. I will also bring you a little bit more enlightenment into the meta layers we are using, the collection of meta layers we are using for Oniro. Then I will hand over to Andre, who will tell you a little bit more about the Oniro distribution specific features, some of them at least, and also talk a little bit about how you would enable a specific board you might have for Oniro. And then we will head over for questions and answers. So if you have seen the talk before from David and others, you might have seen the slide. So don't be worried that we are trying to cramp everything in these slides into like 30 minutes or something. We really want to focus on two specific parts here. On the right side, you can see that it's a BitBake, the build tool we are using, coming from Yocto and OpenEmbedded. And on the left side, you see the red box with a few of the layers with different components we are actually providing with Oniro, we are consuming with Oniro, and we will go into a bit more details on what we are doing there. So Yocto and OpenEmbedded. Normally what I would do in this situation, I would want to have a show of hands of the audience to understand who's actually familiar with Yocto OpenEmbedded or has used it before and what kind of areas and so on. But that's not really possible right now with the virtual environment here. So I will try to wrap it all together so we are all starting from the same base, basically. This is my almost too short overview on these. So the Yocto project is a collection of component and tools, basically. One of these tools is the BitBake build tool, and another is the metadata format for all the packaging. Both of them originate in the OpenEmbedded project. And the metadata format are basically receipts to build instructions and general metadata for packaging. So if you have done any packaging for other distributions, most of the things are kind of familiar. So you would have can decide things like where a specific file is installed, if you have want to edit or have provide specific configuration files based on a distribution policy, or what kind of systemd services or something else is started by default on an image and stuff like that. You can tweak all these things and make sure everything is building correctly and make sure that you integrate patches and so on, all these things. And then one thing Yocto brought to the table when merging together with OpenEmbedded was introducing the concept of layers. So this brings a lot of modularity and flexibility into the play here. So you can really pick and choose what kind of components you want to use, be it software provided packages, hardware BSPs, or all kind of things. And then you have your own layers where you would have do your own integration or differentiation, stuff like that. So that really brings a lot of flexibility to the table. But the Yocto project also is offering other things like developer tooling, for example. So DevTool itself is one of these, is an example for this. So it helps you to create, modify, or upgrade receipts, which can be done obviously with just a text editor, but this task can be really daunting and error prone. So it's really good to have some kind of developer tooling around this. So what really is appealing for us to Yocto OpenEmbedded is that it's really a well-established and supported build system for embedded. It's kind of a de facto standard, industry de facto standard for that. I think I started using OpenEmbedded 2005, and Yocto merged, I think, around something like 2012 or something. Don't name me down for the days. So that's really a long time, and by now it really has gained a lot of traction in community as well as in commercial identities. So you can have commercial support, you can get training, but you can also just do it on the community side and have a lot of interactions there, a very vibrant community, making sure that things get reviewed and enhanced over time. So to explain that a bit more, so Oniro is based on Yocto-based. A lot of the things we are doing is based on the layers of all the concepts they're having, and we are adding to that. And we are actively working on upstreaming the changes we do. So some of them are just for our distribution, so they are not really worthwhile to upstream, but like core concepts and core changes and stuff like that, that is what we are working on to upstream. So after explaining what Yocto-based basically is, like, let's have a look at what we would do to actually use it in our case. So this is really a nutshell of how we would build an Oniro-based image. So you can, if you look at the commands there, you will see that we will create and we initialize a repo workspace. Then we clone all the repositories. We initialize a build directory for a specific build flavor. And then we are ready to run bitbake to create the image for a specific machine. So in this case, we would just create a directory called Oniro project. And then repo init and sync will take care of cloning all the repositories, placing them in the correct location, so everything is like available and working together smoothly. So to initialize the build directory using a script that is delivered together with Yocto, it's OE init build environment. And so we're creating a new folder, basically build Oniro Linux, where everything will happen inside. For that to happen, we will use a template. In this case, it's a Linux template for the Linux flavor. I will talk about that on the next slide a bit more. And once that is created, we will just fire up bitbake. And what we do here is like we want to create an Oniro base image. And we want to do that for a machine. And the machine in this case is a kernel-based machine for x86 64-bit. So on the right side, you can see the directory structure, basically. And now you can see why we use something like repo to get all the things bundled together, because all these meta prefixed directories are different Git repositories we need to keep track on specific branches and maybe even revisions and stuff like that. So make sure everything is in place. That is why we are using that part. Okay. So I mentioned on that before, the build flavors. So we aim to run on Linux as well as Zephyr, and we also have an experimental support for free RTOS, and we have work-in-progress support for the RTOS kernel. And all of these things will have a specific layer where all the abstraction integration of the operating system kernel is actually happening. I mean, besides Linux, which is already part of the Yocto build system itself. But on top of these meta layers, for example, meta Zephyr, you would still need to have like some sane default settings to make everything run very smoothly and building correctly. So for this, Yocto has a concept of templates. Basically, just a few text files to be placed in the correct location. That would be a local conf, which sets things like the distribution and also things like caches and download stuff and so on. So it's all like making sure that everything is set up correctly. The same is for the BB layers file, making sure that all the layers we need for this specific build are in place. And to ice that up on top, we have like a conf notes file, which is just hints for the first time users to understand what kind of images are available, what kind of machines are supported, and so on. So this is really how the build flavors are playing together to bring the different layers in place and making sure everything runs smoothly. So after talking about the flavors, we now can go a little bit more into the layers we are using right now. So if you start on the right side, you can see that we have different software support layers, basically. This could be very specific to things like over-the-air updates, where we would use something like MetaRouc. It could also be specific to networking services or something where we use meta networking. But it could also be just programming languages, Python, Perl, stuff like that, or specific parts for security, or even like the whole toolchain, like meta-clan or something like that. But we also have layers just for hardware support. This could be higher level layers like Meta Intel, where a lot of the Intel support is sitting, but also it could be specific to specific boards like Meta Seco Intel, for example. Like for their own Intel boards, they will use the Meta Intel layer, but like have different parts and changes to that. We have that for different Intel and ARM boards. We're also looking into RISC-V support, and obviously popular systems like Raspberry Pi and so on are used here. So for the situation where you want to bring your own board or your own SoC into Oniro, my colleague Andre will talk about that a bit later in the talk. But basically what we are looking for is like getting a new layer for the BSP support and then hooks it up into Oniro. So switching more to the left side here, you can see where the core parts of the Oniro distribution are. So really the parts where we define what kind of policy we have, what kind of, for example, the build flavors are sitting there and the manifest files and stuff like that. So that's not a real layer per se. It's more like holding all the things together, what we need to build a distribution. But we also have our own layers basically for Oniro core, having like core services, making sure that all the configuration files are adapted to our needs and so on. Then we have blueprints where we create demos for different blueprints basically to decide what components go in there, create specific images for that and so on. And then we have the staging area for things that are not yet ready to get upstream to Yocto OpenEmbedded, but we still need to work on that and still need to have it be part of our distribution. So if you look at the layers from a different perspective, it's kind of like an onion where each layer builds up on the layer before, right? So the distro core layer would be, well, the core, obviously, where all the things are sitting together. Then around that, you can wrap like the kernel layers we have for Linux, Zephyr, FreeRTOS, and LightOS. And built on that, you would obviously need a lot more components, middleware, frameworks, development languages, and all these kind of things that might sit in a framework layer, but come from different areas, basically. And on top of that, you would have applications to consume all these layers and all the services and APIs they're offering, basically. And with that, I will hand you over to Andre, who will give you a bit more of an understanding of some specific features of our distribution. So, and with that, Andre.
Thank you, Stefan. I hope you guys hear me well. So when I posted a link to the discussion on LinkedIn, I recommended you guys to have a cup of tea with you guys. So by that time, we should be halfway in that cup. And that means we are halfway in the talk. Obviously, you could have chosen any kind of tea, but Earl Grey is just the best. Now, joke aside, Stefan showed you the shape of the ecosystem. The architecture is basically an X-ray of what you expect in terms of technical structure. But now that you know how it looks, you're probably interested in what it does. What is it attractive about this ecosystem? Why should I invest into this ecosystem? How can this ecosystem address my use cases? As mentioned, the architecture is based on Yocto OpenEmbedded concepts and primitives. Now, Yocto became the industry standard due to a fact that it's also considered its biggest flaw: generous flexibility. This caught up quickly because the exposed primitives were so simple and diverse that could be applied to any use case. I did mention it's a dual-sided sword though. Its flexibility comes with the disadvantage of making it difficult to bootstrap products without reasonable knowledge of the build infrastructure. Now, Oniro is that step forward. It creates higher level primitives that provides opinionated defaults and policies while keeping the Yocto OpenEmbedded architecture flexibility in place. In other words, it provides you a fast lane forward for you to concentrate on your business logic. So features, system updates, OTA primitives in that regard are baked into our platform. The root file system is read-only, so that gives you assurances of runtime of consistency, and it aims at helping system updates for atomicity. The platform also handles OS distribution state. It models the partition table in a unified way, and it also gives you an easy integration process for your hardware support. Cool, so system updates. Next slide, please. In Oniro, we have designed OTA primitives that have a set of fundamental requirements. They align with production level runtime assurances. They align with concepts that are known in the industry and are default in these kind of features. For example, atomicity and durability. These are assumed by the design. The primitives are also clear and defined so that you can easily plug in additional hardware support. We use existing open source software to build our update stack. For example, Rauk is one of the core components we use in that regards. The update procedure is image-based, making it aligned with the industry standard. It's easy on your bandwidth by providing functionality in terms of deltas, and it maintains limited hardware assumptions with defined interfaces for extensibility. To handle support for atomicity and deltas, the platform defaults to a read-only file system. For production-like environments, we define that as squashfs, while for development, we set the root file system as a read-only mounted ext4. Once this is in place and defined as a feature of OS, we need to handle writable areas at runtime. This can be of two types. Stateless, usually TMPFS mount points that are by design lost over reboots, and also stateful, which manage data that is required to be persistent over reboots. So that brings us to the next feature, state management. This becomes an OS primitive to deal with runtime assumptions and needs for persistent state. We designed and implemented this at 3 different levels. System level, where system services store persistent data, for example, SSH host keys. Device level, where manufacturing data that is populated under the manufacturing process, for example, MAC address configuration. And the last level is application state, which is a catch-all for persistent data needs of various applications. Now, what's important about this is that you have full control of your services rights. So it's either TMPFS, so it's going to be lost over reboot, so you don't have to deal with atomicity and durability in that regard. It's read-only, so you can't write anyway, or it's handled by the state management feature, so you know exactly what you're giving access to the services you have on your product. There are more features the platform offers. So I'm only going to mention a unified partition table that removes runtime assumptions on it. And as a last point, a unified Linux kernel 3 with configuration functionality that gets you out of the weeds of countless kernel forks. Cool. So X-ray done, short feature list, I've just done it. For the last part of this presentation, I'll try to dive a bit deeper into how a BSP can be integrated in Oniro. Now, as you see here, the base is quite straightforward. We have the Yocto OpenEmbedded build metadata along with the Oniro build metadata that creates a base layer, on top of which we add existing BSP support for our default board support. That is integrated in our CI pipelines and provides you the assumptions of supported boards. So now, how do you plug a new BSP into this platform? So Yocto has this concept of a layer. It was mentioned before, that is basically a collection of build metadata. In the case of a BSP layer, the most important metadata is the machine specification. That is basically a file that defines the target you're going to build for. So I have here an example of Meta Raspberry Pi, which is a BSP layer for the Raspberry Pi family of boards. So you can see here there is a bit of boilerplate, you have type, name, and description, and it starts by defining as well later the default tune, which is the configuration of the toolchain. It also sets the serial console, so you have the device node and the baud rate. You also have the U-boot machine, so the U-boot recipe knows what configuration to take into consideration for this specific machine. ARM stub is something very specific to Raspberry Pi. I'm not going to get into these details for you because it defeats the purpose of this specific presentation. The machine configuration is meant to define the toolchain configuration and select the BSP-specific packages for that specific machine. Taking the same example, for example, for Raspberry Pi, the virtual kernel is going to be selected as Linux Raspberry Pi. There's also selection for different graphical stack components like EGL, Glass2, libgl, and so on and so forth. So once you have the machines in place, all the BSP layer needs to do is to provide BSP-specific recipes. Following the same example, you'll have to have a Linux Raspberry Pi recipe. So the build system knows what to build for that provider. You will need to have the userland for the graphical stack, and so on and so forth. Now, most of the times, you don't even have to do any of this because Yocto has an index layer that centralizes all the existing layers, and there is a very high chance that your target of interest is already supported by an existing BSP layer. When that's proves to be wrong, Yocto also provides extensive documentation way beyond my surface scratching in this presentation. So now you have a BSP Yocto layer. All that is remaining to do is to plug it into your bblayers.conf, and the Oniro build infrastructure will consider it as supported machines. Great. So what now? Well, first of all, talk with us. We have an IRC channel called Oniro Project in LibreChat. Talk with us, discuss your use cases, see what is interesting in the platform, see how this platform can help you. And when you have an idea of that and you connect it with us, poke at our code. We have a GitLab instance at booting.oniroproject.org. Get accustomed with the build structure, get accustomed with the code, with the repositories that we have there. And once you have a connection with us and you're comfortable with the build infrastructure and the code generally, join us and contribute. Make your use case part of the platform. Make the platform address your use cases. Great, so this should be our last slide. It's a Q&A slide, so I'm going to read some of the questions I've been followed with. So the first question was, do you have any plans to look at Azure RTOS? That's a former ThreadX. As far as I know, Stefan is here to confirm or not. There is no plans at this point. We haven't discussed this. But it's one of those things that, based on the community needs, we could look into.
Yeah, to add up on that, it's basically the same as we have been doing with RTOS, for example. So there was an interest from partners, and they wanted to see that. And then there was work going into that. So if there is interest from the community or companies or whoever joins the project, it really doesn't matter much, to have support for this, then it definitely can be put on the roadmap. But it's not something where you just put something on the roadmap and someone else will do all the work. So it has to be driven from someone. That doesn't mean it has to be all the work done by one person or one company or something. That's obviously shared in the end. But there have to be use case and there have to be a driving force behind that. From our side, we don't have support for, we don't have it on the roadmap yet, but that can change.
Yeah. Question number 2, do you have hardware support layers for Cortex for M4 and M7? Stefan.
Yeah, I mean, basically what we have there is we are using on this kind of Cortex, we're using Zephyr. And so we have all kind of boards that are supported there. At the moment, we're using Meta Zephyr, which has a very limited support of boards because you have to manually add all of them. So we have been doing that for every board we needed support for. It's not really a big problem or a time-consuming thing. But we're also looking into how we can extend that a bit more, that we have out-of-the-box support for all of the Zephyr supported boards at that point. For all other kind of boards that you run on these kind of MCU-based systems, again, that would be RTOSs. That could be something like FreeRTOS. It could be something like LightOS or like Azure RTOS or something like that. So.
Yeah, just to add something there, we are revamping the implementation of Meta Zephyr. So the problem that Stefan just mentioned, the fact that we have to constantly maintain the machine support in the layer, is going to be addressed by doing generators. We are going to dynamically generate statically, but with a known automatic way of generation of machines. So that's something we are looking into to leverage on. Also on Cortex M4 and M7, I think there is some support in LightOS as well. So not only Zephyr, but also LightOS. Cool. So that's question number 2. Question number 3. Is there OTA for Zephyr LightOS type of devices that are not using Linux? Okay, so at this point, the implementation of the OTA primitives that we have as of today are only targeting the Linux kernel or a Linux environment distribution, basically. We are going to, so our next step is going to be Zephyr. So that's going to be our next OTA step. For LightOS is something that we will definitely going to look into a bit later on the roadmap.
Yeah, so on the Zephyr side, but also potentially for other RTOS-based systems, there's the MCU boot project, which could be a base for that. We haven't fully decided on that yet. We need to start looking into that. We started this on the Linux side, because that's also a bit more complex in different areas, I would say, than on the RTOS side. So we also have in mind that we might not be able to do like system updates the same way we did on the Linux side. So we might need assistance from a different part of the network, for example. So we have this concept of like direct software updates and assisted software updates for like small devices, which might not be able to have like enough resources to do it like completely on their own.
Yep, and the last question, I still think we have a couple of minutes, so I'm going to go ahead with it. How have you approached the abstraction issues in OpenEmbedded when moving from Linux kernel to other RTOS kernels? How clean is the Zephyr, LightOS, etc. support in this regard? So I've mentioned this in the presentation. OE has this feature. It's also, again, one of his biggest flaws of being extremely flexible. And because of that, the integration of other kernels was not as complicated as you think. Meta Zephyr, was out of the box. The tool chain setup in the build system is quite separated, and the interfaces are clean and easy to use. So I would say it's not that complex, and it's pretty clean. On LightOS, it's work in progress as of now. So that being said, again, Stefan already mentioned there are some current issues with the Zephyr implementation of the support, namely machine definitions, and not only that, but there are things that we can improve, and we will be working on in the next steps.
Okay, so really quickly on the last question we have is a roadmap available? So there was a session before our talk from Davide and Adrian. I think there was a roadmap in there. If not, we need to make sure to bring something up on your project page, what we have there. I don't have the link in my head right now, but we have something like that, and we need to publish that together with all the other slides and material we have created here. So please check back later on the onioproject.org page. We will make sure that something will appear there in the future.
Cool. And I think that was our last question. We are also just a short under 1 minute to the end of this presentation.
Yeah. Let me say thanks a lot for all the questions. I mean, it's really great to have like this kind of interaction, even if it's a virtual event, to have like in-deep technical questions coming in here, and we're happy to provide answers. So the IRC channel is still open. You can just go there, join, and talk to us. Thanks a lot.
Thanks, guys. Have a good one.